Okay, I just want to take a few minutes here and talk through the Chapter 7 and Chapter 8 free response questions with you guys. I think when we get to the Chapter 8 free response question, that one should seem pretty easy to you. That has to do with confidence intervals, something that we've talked about recently here. But these first few from Chapter 7 might feel a little bit more difficult to you. So on this one, this is talking about the depth from the surface of the Earth to a refracting layer beneath the surface can be estimated using methods developed by seismologists. One method is based on the time required for the vibrations to travel from a distant explosion to a receiving point. Now, I tried to color code some things here to make this a little bit easier. Everything in yellow is representing what's called the depth measurement M, and that's calculated by taking the sum of the true depth, D, and the random measurement error, E. Okay, and so you can see this is showing you how they're getting that depth measurement that I highlighted in yellow. Okay, it says the measurement error E is assumed to be normally distributed with a mean of 0 feet and a standard deviation of 1.5 feet. So I went ahead and kind of grouped all that information right here, labeled that in blue. So that's everything that has to do with that measurement error. Okay, the question is, if the true depth, okay, that's our D here, if that is 2 feet, okay, so we know it to be 2 feet at a certain point, what is the probability that the depth measurement, that's in yellow, would be negative? Okay, so we're going to be substituting a 2 in for the D. Okay, and what I'm really needing, if I'm going to do a probability question, is I'm really wanting to try to get what is the mean, what's the standard deviation for the depth measurement so that I can use normal CDF here. Okay, so I know that the true depth is 2, so it's like I'm adding a constant to the random variable E, which is the measurement error. Okay, well, when you add a constant to a random variable, it does impact the mean. Okay, it affects the measures of center. It will not impact the measures of spread when you add or subtract, only when you multiply. So if I add 2 to this random variable, that's going to make the new mean for the depth measurement to be 2. That's how I got a 2 here. However, if I'm just adding a number to a random variable, that's not going to change that random variable's standard deviation. That's why I have the exact same standard deviation here. Once I have this information in place to represent my depth measurement, I then can go ahead and answer the question, what's the probability that it would be negative? Well, that's basically what's the probability that it would be less than 0. So I'm doing the typical normal CDF. You can see how I have these labeled. And I come up with the probability that a single depth measurement would be negative is roughly 9.12%. Okay, you're going to see in this free response question how these responses tend to build on each other. Okay, so when we get down here into part B, it's now saying, let's say that instead of taking a single depth measurement, you took 3 independent depth measurements at the exact same point where we knew that the true depth was that 2 feet. Okay, what's the probability that at least one, there's that buzz phrase, at least one of these measurements will be negative? Okay, when we see the phrase at least one, we immediately want to think of this little kind of setup here, that at least one, the probability of at least one, is typically found by taking 1 minus the probability of none. Okay, so if we're saying what's the probability that at least one of the 3 would be negative, then we really need to calculate 1 minus the probability that none of the 3 would be negative. So we need to think through, how could we get the probability that just 1 would not be negative? Well, up here in part A, we know the probability of 1 being negative is 9.12%. So if I want the probability of none, or that 1 is not negative, then I'm going to subtract that. This right here is the probability that one single depth measurement would not be negative, okay? But I'm taking 3 measurements. So you'll notice when I filled this in here, I have to put in the exponent, I have to cube that, Okay, and then I just type that into the calculator and I get roughly 24.94%. Could also have done this using the binomial CDF. Okay, now here's where you have to be really, really careful. If you read very, very closely part C, it says, what's the probability that the mean of 3 independent depth measurements taken at that same point where the true depth is 2 feet will be negative. Now, if you don't read this carefully, you might think that this problem in part C is asking exactly what part A was asking. But in A, it's talking about a single depth measurement. What's the odds of just a single depth measurement being less than 0? We use normal CDF with this information. When you're asked a probability question about whether an average would be, in this case, negative, now we're talking about the sampling distribution. And so we need to recalculate here and say, well, if we were to go in and take groups of 3 measurements at a time and then average those 3, put those on a dot plot, we learned that the very center of that dot plot for that sampling distribution of X bars is an unbiased estimator. It should be exactly in line with what the population mean is, so that's 2. Now on the formula sheet, you're going to see there's this formula for the standard deviation of the sampling distribution for X bars, and that is taking the population standard deviation, that 1.5, and dividing it by the square root of n. And in this case, the n is the 3 samples, the 3 different depth measurements you're taking. So that generates a new standard deviation that should be used in this spot here when you do the calculation. And you can see then how I got that the odds of collecting 3 samples, averaging them, and their average being negative is roughly 1.05%. Okay. On this next one, I'm thinking that this question was actually on one of the tests that we had. This is talking about big town fisheries. It says they recently stocked a new lake in a city park with 2,000 fish of various sizes. The distribution of the lengths of these fish is approximately normal. Big Town Fisheries claims that they're claiming their average length of their fish is 8 inches. Now, if the claim is true, which of these 2 following situations would be more likely? Okay, is it more likely to take a random sample of 15 fish and get that their average length of those 15 fish is greater than 10 inches, or would it be more likely to take a random sample of 50 fish and their average length would be greater than 10 inches? Okay, now the key with this is recalling that this is the formula for how you get the spread of a sampling distribution, which is when we're talking about taking samples, calculating their average, putting those averages on a dot plot. Okay, we talked about when you increase your sample size, okay, so as the sample size increases, what that does to your sampling distribution is it causes it to decrease. If you think back to that penny activity we did, when you take larger and larger sample sizes, it causes that sampling distribution to have much less variability, okay? Therefore, if you were to take a smaller sample size, like 15 fish, there would be more spread, more variability. That would increase the likelihood that the average length is greater than 10 inches if the truth is that it's really 8 inches, okay? Because the bigger samples you take, the closer you would expect your averages for your samples to be close to 8 inches if that's really what the truth is. Okay, so we would say that it would be the smaller sample size that would increase the likelihood of you getting the averages to be more than 10 inches there. Okay, now in letter B, I feel like they threw a little bit of a curveball at you. You had to read very carefully. It says, suppose the standard deviation of the sampling distribution of the sample mean for random samples of size 50 is 0.3 inches. So they are already giving you the standard deviation of the sampling distribution. You don't need to plug that into the formula or try to take something divided by the square root of 50. They've done that by, what they're calling this up here. So you just need to take that number Make sure that gets plugged in right here. I should have labeled these. I'm going to go ahead and throw that here. This would be mean. We call this standard deviation. All those calculator inputs have to be labeled on the test. Okay, and then we could see that that's the likelihood of getting an average length, okay, a mean length, an average length of under 7.5. Okay, and then down here it says, now let's suppose the distribution of fish lengths in the lake happened to not be normal. Okay, so it's not normal, but it had the same mean and the same standard deviation. Would it still be appropriate to use a normal distribution to compare the probability in part B? Okay, justify your answer. Well, if you look closely at what our sample size was, the sample size was 50. So that's why we're saying it's still okay to use the normal calculations because it's greater than, I should have said greater than or equal to 30. And we can cite the central limit theorem as saying that's large enough. Okay, all right, and then down here, this was talking about if there was a shortage of flu vaccines. They took a survey. It says in a random sample of 2,350 vaccine-eligible people, 978 of the 2,350 people had actually received the flu vaccine. So this gets labeled as p hat. This is a sample proportion. Okay, if you want to write that as a decimal, that's fine, 0.42. Okay, do not forget this do step. You need to state what you're estimating, and this is absolutely crucial. You are always framing your confidence intervals around trying to estimate a population parameter. So these are either mu's or they are p's, okay? And then you're just going to grab from up here in the directions. We are making a 99% confidence interval for the true proportion of vaccine-eligible people who had received the flu vaccine. We're saying at a 99% confidence interval. Okay, we've got our checks, random, 10% condition, normality, the large counts condition. We're calling this a 1 proportion Z interval. You'd be more than welcome to run this test on the calculator if you choose, or you could use the formulas that are on the formula sheet here. Okay, it mentions that, by the way, when we do this, you always have to include this bottom part here. We're 99% confident that the interval that we constructed here captures, use context, the true population proportion, and so on. Okay, now I didn't read this part down here, but you have to make sure on the test you're really careful. It says use your confidence interval to comment on the belief that 45% of the vaccine-eligible people had received the flu vaccine. Okay, so in the end, we want to make a statement here and say, well, since 0.45 is not really a plausible value, then it's unlikely that 45% of the vaccine-eligible people received the flu vaccine. Okay, and then this last part, part B, this is where we're saying, well, let's say that Canada tried something similar. They're doing a 99% confidence interval for the proportion of people who received the flu vaccine. They constructed that, but they want to know what is the smallest sample size that they could use to guarantee that their margin of error would be less than or equal to 2%. Okay, remember, here's the formula. This is the piece right here that is the margin of error. That's really the part that like comes in front of the plus or minus when you're doing the confidence interval. Okay, this is your margin of error. Now, when they don't give you a value for your proportion, you are supposed to use 0.5 for the probability of a success, which also in turn makes 0.5 the probability of a failure. Okay, so you just use that as what you're plugging in there. Okay, I got 2.58 by doing this for a 99% confidence interval. We set that less than or equal to 2% is all the more they want their margin of error to be off. The rest of this is just using algebra to solve backwards. You can round this up then to the nearest person. This would be the absolute smallest sample size that they should use if they're wanting to guarantee that their margin of error is under or equal to 2%. Okay, again, hope that you guys are all doing well. Please reach out if you guys have questions on anything. Take care.